Okay, so the recording is working and yeah, we're live. Okay, so I welcome you all to another doubt clearing or problem solving session for the course Smart Grids Basics to Advanced Technologies, being taken by Professor N.B. Padhy and Professor Premlata Jena from IIT Roorkee. I am Swastik Sharma and I am a TA for this course. Okay, so we'll start. I mean, people will join in the meantime. Otherwise, it's freely available on YouTube, and I will be always, I will always be able to help you out in the comment section of the YouTube video where this is going to be uploaded. All right. So let me share my screen. All right. So last week we were discussing about wide area monitoring systems, and we discussed in at length about uh, how the new generation PMUs are able to convey transient or dynamic are able to give dynamic or transient observability to the system operators, which is not possible with SCADA, given that they are because of low resolution they are not able to provide that transient or dynamic data needed. So we were discussing about VAMs and we discussed about phasor estimation, frequency estimation that is used in PMUs, and then at the end we were discussing about over currently relays and how they are used. Today we'll first begin with the a simple concept, that is islanding detection in microgrids, because that is important concept to understand why smart grid protection is needed at uh, protection is needed for the smart grids, and how these protection systems are being made more smarter in general. And for that we should first know, from the first class we talked about what exactly is a microgrid. So a microgrid is an energy power system which is able to operate locally or without the need of a secondary or main grid. It can operate conjunctly with both main grid and without it, but a microgrid is able to sustain itself, sustain itself in a way. So this here is a diagram of a simple microgrid. As you can see, this microgrid, it's connected to the main grid, which is which is through a point of common coupling, which is a PCC, which is this point. So this point is the point at which the whole microgrid is connected to the grid, and it exchanges power through this point with the main grid. And as you can see, there are many loads, and you have generation available at the distribution side, which is through diesel generator or DFIG or PV arrays, or your biomass generation, your micro hydro, your micro turbine, or your BESS systems or fuel cell, right? So all this localized energy is able to help you to sustain yourself even when the grid is out of, the is not in contact with the system. This kind of, operation is generally called as islanded mode of operation. So what is islanded mode? It's the mode, just a second, I have to do this every time. Okay, so islanded mode of operation is nothing but operation without being connected to main grid. So why is that? Why would you want to, sustain yourself without main grid? So there are many reasons. Let's say that something happened to the point at the point of common coupling and the grid is no longer available for you, right? And there are a lot of critical loads that are there at the like for example hospital is a critical load. So when I say a critical load, that they require power at all times. So in general, a hospital, a school is generally considered to be a critical load. And as you can see that many of them, these hospitals, they have DG sets. Right now in India, these hospitals usually have DG sets, which are diesel generator sets. These are not sustainable in nature. They are installing PV arrays and other renewable energy generation, renewable energy based DRs. But you'll see that all of them can can be used to power local loads as well, to which they are contained to, like for example a hospital or a school. Right, even at IIT Kanpur, if let's say the power is not available from the main grid side, at each department we have diesel generator sets and battery energy storage system and thermal energy storage system as well, to sustain the loads which are required. We can't function without electricity. There are a lot of loads that require electricity, right? So so that is how a microgrid operates, right? And it can be seen as kind of like a miniaturized version of a version of a traditional grid, right? So like traditional grid has generation and loads, we too in microgrids have generation and loads, right? So it's like kind of like a miniaturized version, not like in gigawatts, but like in megawatts we can sustain the loads. And because of the presence of microgrids, we are able to operate within a defined area, and a defined area which is also called as a local area, right? So they can operate and control a local area load. Right, and there are a lot of benefits. Not only they can power the critical loads, but they have a few benefits as well. Let me make space. So I guess let's write here. So benefits. So one, it increases resiliency. What I mean by resiliency is that the ability to sustain outages, right? When let's say there is a power system outage, what happened during 2012. So there are critical loads. To power them, we can have these microgrids which can act as sort of like a resilient infrastructure to empower critical loads during times when there is outage in the main grid, right? Second is sustainability. So they support sustainability, right? Because if microgrids tend to use these um, uh, uh, renewable energy generation technologies like solar PVs and small scale wind turbines, we can it's called a sustainable form of electricity generation. And due to this, what happens is naturally the efficiency of the system can be increased, right? Because we are able to sustain the load even during outages, the efficiency of the system efficiency of the system also increases to empower the loads, right? So these are some of the key areas where microgrid plays a role. So there is an extended definition which ma'am has given in her slide. So it's according to IEEE 1547, that governs the whole DRs and their interconnection to the main grid. And you'll see over there that everything related to everything from the aspect of what kind of DR can be operated, the voltage level and everything can be seen. I will urge you to go to IEEE's website, and over there search for this 1547 standard, and it's available freely. I mean, otherwise you'd had to pay substantial fee to view that, but right now it's available freely as last that I checked. But if you are not able to access it, let me know, I'll send you the document. Right. So this is where the benefits of microgrids are. But with benefits come a few drawbacks too, right? So as I told you, they can work in both modes, right? Grid connected mode of operation as well as islanded mode of operation, and they have a transition to island and reconnection modes too, right? But in both of these modes, there are certain dynamics that come into play, right? Which can affect the overall power system operations, which can affect the overall power system operation, and that has to be comprehensively studied. So as I already told you how a microgrid looks, this is how a microgrid looks. And what I meant by islanding was this only, that let's say, so yeah, just a second, I'm audible, right? Yeah, my voice is audible. Okay. So as you can see in this system, the same, not the same, but microgrid is present where we have fuel cells, some wind, some PV generation system. Data center we have EVs loads, and we have batteries too, and we have power coming from the main grid too. And let's say by some fault or something happened which tripped the the circuit breaker at the PCC, and now the main grid is no longer available, right? So the localized generation that we have from PV, wind, and fuel cell, and even battery, can be used to sustain the loads that are present, such as these the data center, the EV, and the any other loads that are present at the microgrid, right? So this is what I mean by islanding, that when the main grid is no longer available to power the loads inside the microgrid, right? So this is what islanding is, and there are different types of islanding too. Like for example, a microgrid can be of different kinds, right? At different voltage levels, there can be different kind of energy generation devices available as well. Let's say, for example, at the distribution substation, this is the distribution. Just a second. Yeah, this is the distribution substation, right? Here, the bulk supply is connected. Like when I say bulk supply, the power coming from the large generators is coming, right? And there are many feeders connected to it. If you remember, I showed you this SCADA diagram of IIT Kanpur, right? Over there, there were many feeders, just like this. This is one. This is one overall view of how a distribution system looks like, right? There are many feeders, and over there, there is this section of feeder available to us, right? Here we have multiple houses connected to a single feeder connection where there is localized generation available, and we can have one household too which has its own generator too, right? So this generator empowers this household, and this generator empowers a group of household, right? So there can be a single customer microgrid where there is only localized generation available to a single customer only, and there can be a partial feeder microgrid where there is a localized generation available for multiple customers. And there can be a full feeder microgrid where there is a bigger generation connected to directly to a feeder, which can empower the whole feeder microgrid. And we can have a substation. Let's say, for example, this is nowhere. PCC is no longer into the sorry. Main grid is no longer in picture. We have other generation available to sustain the loads, right? So these are different kinds of islanding available at the distribution side, right? Now, what happens is that this islanding, we need to detect this islanding. So there are reasons why we need to detect these islanding. Like for example, let's say I am connected to I have a microgrid. I am a microgrid operator. I am connected to the main grid, and by something happened, some fault took place, and we were islanded for a couple of hours, and then suddenly the main grid was available, and we connected out of the blue, right? We just simply connected to the main grid. We didn't do any kind of any exercise to to connect to the main grid, right? There is certain procedures laid out in the IEEE 1547, which I also asked you to take a look at, where you will see that there are different procedures in which you have to connect to the main grid. So let's say some islanding happened that you could not detect, some fault took place, and you are now behaving as an islanded microgrid. Now there can be certain uh, issues that can arise out of that. One is out of phase reclosing. Let's say some unintentional islanding occurred, and similarly unintentional reconnection also occurred, right? And now when you reconnected, right, it could so happen that the frequency that the microgrid's PCC point, let's say, let me draw this circuit now. I'll just take this. um, Copy. Okay, let me show you. Okay, let's say I'm talking about this microgrid, right? So it can so happen that this is the PCC, right? Point of common coupling. And it may so happen that when it was islanded or it was behaving on its own, there could be some frequency that could have, related to how these loads were functioning. and the main grid will have some frequency, right? Both of them are not interconnected right now, and they can have separate frequencies too. Now, at the time of unintentional reconnection, what happened? These two frequencies, if they are out of sync, let's say this is at 49.4, which is quite low. Oh, yeah, it's 49.4, let's say. And this is 50.3, right? And you're trying to reconnect at this frequency, right? So what usually happens is that due to different operating frequencies, we can have voltage and frequency going out of synchronism, which could cause power quality issues at the distribution side, right? And this is not at all feasible for how it should behave. I mean, the microgrid and the main grid must always be in sync with each other. Otherwise, what will happen is power quality issues will arise. Like, for example, there can be unintentional voltage surges or swells, and there can be frequency deviation, frequency dripping below to the limited, or sorry, to the uh, to the lower limit of the operating limit, right? So this is something that happens, and this happens when there is out of phase reclosing or out of improper reconnection, right? And this is how degradation in free power quality also happens. So your power quality becomes degraded because voltages, if they're out of sync, and what happens usually is if frequency is out of sync, the voltage will also suffer, not by a big margin, but because there are we will talk about this, how voltage and everything is related in upcoming weeks. But just bear with me for a second, that if frequency of the microgrid and main grid are out of sync, there can be voltage sparks, surges, right? Now what happens is the inverters, let's say this inverter, right? This inverter uses feedback from this PCC. It uses a feedback to be able to match the frequency of the voltage levels or the frequency of this point of common coupling, right? Now this inverter could also go out of sync, and this could cause unintentional power quality issues like reactive power voltage falling down to the lower limit or something, some power quality issues could arise. So voltage and frequency instability can happen. Next, grid protection interface. Now, let's say there is a mismatch in frequency, right? If there is mismatch in frequency at the time of reconnection, what could happen is uh, there will be voltage surges, as I told, and if there are voltage surges, there can be current surges as well, and this can cause tripping of relays. Relays which are not meant to sense these currents, it can sense these surges, and it can cause unintentional tripping as well. And then, as I already told, inverter control mode of mode switching is nothing but it takes feedback from the PCC, and if PCC is out of sync, the inverter will also go out of sync, and it will cause power quality issues. Malfunctioning of protective devices, as I told you, the protective devices will suffer. The relays will sense invalid currents which are not, correct replica of what is happening inside the system. And due to these surges, these swells of voltages and frequency dipping below the lower limit, equipment will damage. So when power quality issues happen, that is why you want to limit these power quality issues, right? These can cause damage to your equipment. Let's say there is a huge surge of power coming at the substation, right? At the feeder at which your this is connected, your renewable generation is connected, right? These surge can travel to your devices, which are um, these inverter based DRs or inverters, which can cause the equipment to get damaged because they are not meant to be operated at that surge level. Also, if there is unintentional reconnection, what could happen is, let's say if a person, if I am a crewman, right? I'm working on something, and I thought, okay, the main grid is off and I can work on my microgrid. I'm just working on some high voltage power line, and what happened? Unintentional reconnection happened, and now this the surge of power will come, and the crew and the personal safety will be in danger, and it can be fatal as well. So this is why we should always detect unintentional islanding and reconnection both. And for this, there are different kinds of techniques available, and these techniques uh, work on concepts that we are going to discuss now. So we discussed why islanding detection is required, right? And we need to discuss this before moving on to the smart grid protection interface, because if we don't know how everything is happening, we can't, you know, uh, we really can't understand why this grid protection interface is required. Right, so let's talk about this islanding detection technique. Right, so there are different islanding detection techniques that the system works on. So there are passive, active, hybrid. You must have learned about in this week's lecture videos, but we'll touch upon everything briefly. So what happens is there is when a microgrid is connected to a main grid to supply load. What happens is we take some power from the microgrid and some power from the main grid to supply our load, right? And we can say that, sorry, yeah, right. And now what happened is the supply from the grid, which is PG, it's nothing but whatever left after consuming all of my microgrid's power, right? So this is my delta P, and we were taking this power from the main grid. Similarly, QG is nothing but we are also taking some reactive power from the main grid, and this is the deviations in both my active as well as in reactive power, right? Now, this active and reactive power mismatch can tell you that if let's say my when an islanding is happened, because when PG will go, PG will go away, this extra power needs to come from somewhere, right? If you have to sustain this P load, this extra power needs to come from somewhere, and because there will be this mismatch that arises because the main grid is no longer into the picture, you will be able to detect, okay, my microgrid is now behaving in an islanded mode of operation, right? For this there are certain standards set by the IEEE. So what do they say? They have set points which are over voltage rating. I will just read. So they have over voltage rating of 1.1 pu and under voltage rating of 0.88 pu, and over frequency rating. So over there in the slides, it's taken directly from the standard, right? And IEEE issues it for standards which are set for American infrastructure, right? So they use 60 hertz as frequency. So over there they have used 60.5, I guess. And similarly, in the Indian context, it would be as it is set by CA, it is set at 50.5, and under frequency rating is also set at 59.3, which will be nothing but 49.3 in Indian context, right? So these are the set points. So what I mean by set point is, let's say some mismatch occurred, right? When a mismatch occurred due to active power or reactive power, the frequency and magnitude of voltage, it starts varying, right? And due to this variation, what happens is your voltage starts to, there is a voltage mismatch as well. And the uh, the s- the islanding detection scheme used must detect this mismatch and must report an islanded mode of operation or not by checking the set points of the rating which is used, right? Overrating and underrating. If it is greater than 1.5 or less than 0.88 for a particular duration of seconds. So if you see the standards, it's meant to be operated only for a particular duration of seconds. So last I checked today, it was 2 seconds above 1.1 till 1.2 per unit. And there are different categories of this, categories of uh, uh, the mismatch or the ratings, right? Category 1, category 2, and category 3. You can check it on the standards website as well. So for a particular duration of second, if that is faced, it will say, okay, I'm behaving in an islanded mode of operation, and now I have to do whatever controlling mechanisms I want to employ to make sure my voltage comes back to the safe operating limit, right? And what usually happens is, because we are using some kind of a mismatch, right? And it can so happen that we were disconnected from the main grid, but we could not check, like for example, some deviation happened, and we were disconnected, but the change in delta P or delta Q was not enough when I say enough, it was not outside this range, the over voltage, over frequency, under frequency, and over voltage and under voltage range, right? If it is between this region, it is called a non-detection zone. When What I mean by non-detection zone is that it behaves kind of like a blind spot, where a DER, which is supposed to modulate its infrastructure to support the microgrid's need when it is disconnected from the main grid, it's not able to view that at all. So there is this non-detection zone, which is kind of like a blind spot, right? And our islanding detection techniques must be able to minimize this non-detection zone. It can't be, it cannot be completely eliminated. I mean, research is still going on. There are not researchers which say, but it cannot be diminished to zero, right? Sorry, to a very small region. So there is always some non-detection zone, and if that is the case, we want our IDT or in this islanded detection technique to be certain that this is very less, very minimized, right? And for this, there are many techniques used in literature as well, which are passive, active, and hybrid and communication based. So there are passive techniques, active techniques, hybrid techniques, and just okay, I'll use here, and communication based. So we'll discuss one by one everything. So as I've already added, I don't know why I wrote. So passive, active, and hybrid and communication based, right? So in passive ways, what we do is we monitor electrical quantities, like for example, impedance, voltage, current. We monitor them closely and look for changes. Like for example, if a change has occurred, we will to a particular some threshold, we will monitor that change to, and if it is above that, we will say okay, we are now operating in an islanded mode of operation. So passive, what they use is they monitor electrical quantities. In active, what we do is we inject some signal, some disturbance into the system. So this signal, or we cause the DR to behave in an unstable region to check. Let's say if that disturbance is removed, if it can only be removed if it is connected to the main grid. We'll discuss about it. Just bear with me for a second. So we'll say that if the disturbance is removed, it is connected to the main grid. If it is not, it's not it's behaving in an islanded mode of operation. So what we do, we inject a signal to check if main grid is connected or not. In hybrid, it's just we use both active with passive. So we combine both, and we take the advantages and drawbacks of both to analyze it in certain way that we can use it to our advantage. Last is communication based. So all these discussion, about smart grids, it's about the interoperability, right? The interoperability means the exchange of information between different devices, right? So if we can use some kind of like communication infrastructure, like for example, a relay which can talk to a different relay, if a trip circuit breaker is able to talk to a different circuit breaker to tell, okay, if islanding has happened or not, that is also being, you know, uh, employed in today's context. We'll talk about this as well. Interoperability, right? So in passive islanding detection technique, what we do is we monitor these electrical quantities. Like for example, we monitor if power quality has deteriorated. Just a second. If power quality has been deteriorated, if what is the how is the frequency behaving, how is the impedance looking, and what are the phase angles, how are the phase angles behaving, and what is the sequence components too. So we will talk about everything. And what we usually check is the power quality, which is associated with voltage, frequency, and the impedance. So let's say that the network impedance, when it is connected to the main grid, it sees a different impedance when it is behaving in an islanded mode. We will also check how Rokoff varies. So what is Rokoff? It is the rate of change of frequency, how the frequency is changing with respect to time. It's essentially df by dt. And we also employ rate of change of phase angle. So how phase angles are varying with respect to time, we'll see. So the first and foremost is the is impedance based technique. So what happens in impedance based is, okay, so these are two separate. So this is grid connected and islanded mode. So this is a DG set or any distribution generation available. Sorry, right? And there is some load that we are monitoring. Just a single line diagram of our microgrid. It is connected to this PCC where there is a voltage that is being monitored, which is called the voltage of the point of common coupling. And we have grid infrastructure as well, which is modeled as a point estimate with point based uh, voltage source and point estimates of its resistance and inductances, right? Now the impedance seen by the DG with respect to the power point of common coupling is more, right? There is impedance connected with respect to the impedance of the grid as well, which it will see. And when it is behaving in islanded mode, this impedance it will not see anymore, right? And we can say that when it's islanded, our impedance has changed. So this is one way in which we can detect if islanding has occurred or not. But this is not reliable or efficient. Why? Because there can be times the when the grid when the impedance seen from the grid is very less, right? If the impedance seen from with respect to grid is very less, you will not be able to track the minute changes in these impedances, right? And one more thing, the frequency, if it changes, and there are different changes that are happening with respect to frequencies as well. So if frequency changes, the amount of load seen from the inductor and capacitor point of view is it will also vary. So to track these changes with respect to frequency becomes difficult, and these impedance-based IDTs are only used for smaller or smaller microgrids, right? So this is one way in which impedance-based IDT works. The second is Rokoff-based IDT or rate of change of frequency-based IDT. So in this, what we do is we track how our frequency is varying. Let's say this is frequency with respect to time, right? This is normal operating zone, and our frequency was varying, let's say, within this only, and suddenly it starts decreasing, right? So what it tracks is it monitors how the frequency is changing with respect to time, and it tells, okay, if an islanding has happened or not. So this is one way in which we can check, and let's derive how this has come into play, right? Let's derive it. So the swing equation is used to derive this relation. So swing equation tells, right, the rate of change of frequency, sorry, or rate of change of frequency is related to the torque that it experiences, right? This is the swing equation in its entire sense. That mechanical torque minus the electrical torque gives the change in frequency multiplied with respect to the moment of inertia. So let's convert it in power domain. So we know P is equals to T omega, right? So that means d omega by dt is nothing but Pm minus Pe upon j omega, right? This is one way in which we can write, and this is this is just a simple derivation. I won't go into the the nuances of it. You can always check your power system analysis books, right? Now we know that J is nothing but inertia constant S base. Okay. Inertia constant is half j omega square by S base, right? So this is nothing but J is 2h S base by, is it correct? Is it correct? It's correct, right? So inertia constant is nothing but the rate of change of the kinetic energy divided by the total rating of the system. And if we substitute this in this, we get d omega by dt is nothing but del p, let's write it like that, upon 2hs base into omega, right? And if we convert it into frequency domain, it is nothing but df by dt, which is equals to del p fs upon 2hs base, right? So this is the formula. It's not in pu. When it is in pu, it will only be del p upon 2h, right? So you see that the rate of change of frequency with respect to time, which is Rokov, is nothing but del p upon 2h. So as soon as your power mismatch happens, there will be some change of frequency associated with it, which will cause the frequency to change with respect to time. And the governing equation is given by this. And in pu, if it's in pu, this is in electrical quantity, right? Everything in its quantity domain. So this is how we check. So right, if there is change in if there is power mismatch, the Rokov will always be there. Will always be a positive value associated with it. So this is how a Rokov based IDT works, and we have one more, which is called rate of change of phase angle IDT. So what we do in this in islanding detection technique is we monitor the phase angle of voltage and current simultaneously, right? So what we do is we check at PCC what is del V, phase angle of voltage at PCC, and phase angle of current at PCC, right? So we monitor both of them, and what we do is we check how they are varying. So Rockopa is nothing but delta V minus delta I by delta T. So we know that if there is uh, some islanding will happen, right? So there will be unbalanced conditions, and when there are unbalanced conditions, the voltage and current, the phase angles between the voltage and the current will also change. And if we measure this unbalancing condition as well, we will be able to tell, okay, if our microgrid has switched to an islanded mode or not. So these are some passive islanding detection techniques. Now, what really happens is that these are not sufficient in nature. Sufficient because they have some degree of non-detection zone. For example, in this Rokov based technique, there is we require at least 15% of power mismatch to happen. So if there is less than 15%, we will not be able to check, okay, and we will not be able to tell if an islanding has happened or not. So there is some non-detection zone, some NDZ present in all of these quantities. And how we come at this 15% is by intuition. If you see, like for example, the for a let's talk from this perspective. At a microgrid level, the 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 generation available is solar, wind and other, right? So for them the inertia is very less, and when I talk about inertia is that the mismatch between active power will be huge, because they will not be able to supply the whole power at once. So this huge is between 10 to 20%. if this mismatch is there, right? I mean, if there is this huge gap between them, we will not be able to tell, okay, if some islanding has happened or not. That is why the average of both are taken 10 and 20. That 15% of power mismatch is at least required to guarantee if um an islanding has happened or not, if you're using this technique. So they have their disadvantages. So we have to, the power quality suffers in all of them before we are able to tell, okay, if an islanding has happened or not. So what we do is we switch to an active islanding detection technique. In active, what we do is we inject. Yeah, yeah, go ahead.
So then the turbine will be having significantly more inertia. I mean, due to that, then it will be able to stabilize the pitch frequency better than the solar.
Yes, but if the sequence, yeah, that is perfect. But that is why I've taken this range, not 10 to 20%. But generally, there are not huge synchronous based DRs present at the distribution at the microgrid level, right? So the synchronous generators that you think are bulk generators, which are in megawatt range, right? In multiple megawatts range, hundreds of megawatt range. That is not the case at the distribution level. Sorry, at the DR, the microgrid level. That is why I told you that they are smaller in nature, and when the power quantity is, if the max power rating is smaller, the level of inertia that they can support will also be very less compared to how the traditional generators work. Yeah, you were continuing? Okay. So so this mismatch, it's in a range. I have not given a perfect value. It's a range. It's generally 10 to 20%, which is observed. Even in ma'am's, this video, you would have seen they have done several experiments based on varying H level, inertia constants, and varying this, how the microgrid is behaving by varying the H constant too. And over there, they have seen that for 15%, 20%, so for different power mismatches, what is the Rokov. So you will be able to see over there. That is why I've taken that as a reference for this. So if you have watched the lecture, you will be able to know from, they have done an experiment to get this rough value, rough estimate. So shall I continue? Okay, I'll continue.
So then what will be in the case of solar penetration? I mean, if it is
Yeah,
very sensitive.
so we have to find out. I mean, I can't give you. See, mhm.
Important console.
I'm not able to hear you. Yeah, can you just, yes? Your voice is very less. Can you continue? I could not hear your question.
Am I audible, sir?
Yeah, yeah, now you are. Yes.
So then what will be the situation when there will be more solar penetration? I mean, do
Mm.
we need to have any good inverter for that?
So, okay, I'll tell you what. So, this was not. I'll touch upon this in, when microgrids will be discussed during week 7 and week 8, but still, I'll give you a brief overview. What happens is that there is concept of virtual inertia. In virtual inertia, what we do is instead of operating solar PV panels at their maximum MPP point, we derate them. We derate them and we operate them with a certain headroom. So let's say they are able to give some P max, but we operate them at some P bar level so that there is headroom available, and we can switch or amp up our generation when needed. So this acts like a virtual inertia. So we always do that when we have only inverter based DRs present in our microgrid. So we'll discuss more on how inertia and how droop control is implemented in case of, purely inverter based DRs in the system. But that is how it's done. We have some virtual inertia in our systems to be used as, cases where we will require that much amount of, headroom for us to navigate between different varying frequency levels. So that is why I've taken this 10 to 20% range for synchronous based generators. If I talk about Rokov, for a generator which is at the transmission level, it is less than 5%. So compared to 5%, this 10 to 20% is already huge. So that is why, I mean, you were expecting 100%. It's not 100%. It's 10 to 20%. Yeah, was I able to answer your question? Yeah. Okay. All right, so let's move ahead. So in active islanding detection technique, what we usually do is we inject some signal and we check how this signal is propagating through our system, right? If at all it is propagating or not. So the first thing that we can do is we can inject a signal injection. So in this signal injection, so we should not call it a disturbance as such, but let's call it a disturbance. It's given in the figure. But a disturbance will not be a very ideal way to say it because it's not purely relevant for our disturbance, but okay. So what happens is that from the perspective of this inverter, right? This is a voltage source converter. VSC is a voltage source converter. So voltage source converter is nothing but that is connected directly across a voltage source, right? So what we do is by using the inherent capability of injecting a signal to through an inverter based DRs, we inject this signal, which is I disturbance. And what we see is this I disturbance will choose a path of minimum impedance, right? And what usually happens is this impedance is lower than your microgrid's impedance, right? So your microgrid's impedance is greater than your utility or main grid's impedance. So what will happen is the main grid will take in, or uh, what you can say is will will take in this disturbance and will help in overall operation of your microgrid, right? So this I disturbance along with the harmonics produced by the inverter, uses, so let me touch upon this as well. So inverter, what it does is it uses pulse width modulation to convert DC to AC, right? It uses switches. Let's say, for example, this is DC, right? Pure DC. It's not varying with respect to time. What it does is with by modulating switches, by controlling on and off, I can have positive voltage at one time instant, negative and other, then positive, then negative, and I can make it behave like an AC signal, right? If it is done at a very high frequency level. So this is called pulse width modulation, and it's not perfect AC, but it is close to an AC, and it contains a lot of harmonics. So these harmonics, along with this injected signal, they choose the path of lower impedance and go straight to your utilities grid. So your grid takes in all of your imperfections, right? And it is able to sustain that as well because there is a huge generation, huge, that it's a very wide area, and it is able to take in any kind of disturbance that happens in your system. And what you have at your microgrid's disposal is pure 60 hertz current, right? But let's say this point of common coupling is now open and you are no longer connected to the main grid. Now what will happen? Your 60 hertz signal along with this disturbance, and I should say this harmonics as well, I don't know why they did not add it, everything will go to your will be inserted to the microgrid, back to the microgrid, right? And you will be able to check how your system is behaving. If this signal comes back to you, if you can monitor this signal again, that means you are behaving in an islanded mode. But if you can't see this signal again, that means you are behaving in grid connected mode. To summarize, in grid connection connected, injected signal is absorbed by the grid, while in islanded mode, injected signal can be monitored at microgrid. So my handwriting is poor because I had my finger got cut recently. So excuse that. If you can't understand anything, just let me know. I'll try to rewrite it. Right. So so this is one way in which a signal injection based technique works. Right. So what we do is we are injecting an unknown signal into our system. Right. And sometimes what it can happen is it can get amplified in a certain way, and it can make our system go into a it can make our system go into an unideal state too. It can happen. I mean, it's not something that will always happen. You should always modulate how much you're injecting, what kind of signal you're injecting, but there can be possibilities where this can happen, right? So what you do, you can use positive feed, you can use another active islanding based method, detection based method, which is called positive feedback technique. So what I mean by this positive feedback technique is, what you do, as I've already told you, your inverter, it regulates, sorry, it tracks the voltage at the point of common coupling, right? So it's continuously tracking what the voltage is at PCC. Now let's say that what you do is you change some electrical quantity component in your inverter. Let's say, for example, phase angle, or some voltage, you change that as an output of your inverter, just so that your DER behaves now in an unstable mode of operation, right? So what you do, change the feedback signal to your inverter by some means to make it behave in unstable mode of operation, right? So keep this in mind, that this unstable mode of operation should be reversible. It should not be like it's behaving at an unstable mode of operation for a very long time and it's irreversible. Just so it can be, it's given this much disturbance so that it can, track back if we want to, based on our, own volition. So it should not be like, for example, it's behaving at an unstable rate at a very long time, right? So something like this happens, and what you can do is, you can check, the point of common coupling. You are now inserting some disturbance with this voltage that is being fed back to your inverter, right? And now your inverter is behaving in an unstable mode of operation. Now what will happen is, this PCC or this inverter will behave in certain way that the grid will try to increase the voltage in such a way that it is able to, bring back inverter from its unstable mode of operation. This will only happen when it's in grid connected mode, right? But let's say if it's not in grid connected mode, what will happen is your inverter will behave in an unstable mode of operation for a given threshold of time, and you will be able to tell, okay, if islanding has happened or not, right? So this is one way in which you can use a positive feedback. So that's why it's called positive feedback, right? It is taking this disturbance and this it's increasing or decreasing whatever electrical quantity that it is modulating in such a way that it is affecting the voltage at point of common coupling, so that the grid side does something to ensure that this PCC is brought back to its original, magnitude level. So this is how positive feedback technique works. So we are purposely changing, or making our IBDER, inverter based DR, behave in an unstable mode of operation. So there are some disadvantages with these techniques, and these disadvantages are: one, disturbance can cause, may cause damage to system components. So let's say you are not tracking this disturbance at all, right? And it can be so rigid that it can damage the equipment or cause power quality issues, right? And there is some NDZ as well, non-detection zone, L- uh, less than passive. So it's less than what is observed in passive based techniques, but there is still. Let's talk about how can it be. Let's say that you're in injecting a disturbance which is very minute, right? It's dependent on the scale of your disturbance that you're injecting, or the signal that you're injecting, right? So based on that, it can so happen that it can visualize it like it's a normal mode of operation when it's not. So that is, there is always a possibility of some non-detection zone available, because the scale of the injected signal is not modulated. Right. So this is some disadvantages of your active based islanding based techniques, right? So then the instructor of this course, Premlata Jena ma'am, discussed one more technique, which is based on passive islanding detection technique. So in this, what they did was they tracked the rate of change of negative sequence impedance. So I hope everyone knows what symmetrical components and what negative sequence positive sequence components are. Can anyone quickly, if someone is not if someone doesn't know, just let me know. I can, just give you a brief overview. Does everyone know? Okay. Okay, let's discuss symmetrical components. So so these are usually used to, used for unbalanced systems. When I say unbalanced, what I mean by is that the magnitude or phase angle of voltage or currents are not same across all the phases, and the voltage phase angles are not 120-degree apart as well, right? When it happens, we say that our system is unbalanced. So what usually happens is it can be something like this: VA, so this is VC, so this is VB. So you see magnitude of all three phases of voltage is different, and they are also not perfect 120-degree apart, right? So this is a case of unbalanced system, right? And what we say is that we can break them into three symmetrical components, which can be used to three symmetrical components which can be used to visualize the system as a balanced system. So these are positive sequence, negative sequence, and zero sequence, right? So generally, we should have all positive sequence components. What I mean by positive sequence components is that they follow ABC phase angle difference. Like for example, if I draw, this is VA, this is VC, this is VB, all 120-degree apart, where B is leading phase A, right? So this is how a positive sequence or a perfectly balanced system looks like. But if there is if there is an unbalanced system, we will have negative sequence component where the phase sequence is anti-clockwise. So same thing. It's just let me take this. So right, just the opposite uh, phase angles, right? And zero sequence is nothing but parallel. I mean, they have no sense of direction but only magnitude. So these are zero sequence components, right? So if I write, sorry, right? So these are symmetrical components. When I say symmetrical, you are decomposing your unbalanced, unsymmetrical components into three symmetrical components called as positive sequence, negative sequence, and zero sequence, where positive sequence is usually represented by V1, which is equal to VA plus. So your VB lags VA by 120-degree, right? So we denote a phase shift operator called as EJ 2 pi by 3. This is nothing but a phase shift operator. And since it lags, so it will be A VA plus A square VA, right? Because it leads, and minus 120 degrees nothing but 240 degrees in lag. This thing is 140 degree, 240 degree. So this is how you write a positive sequence voltage with respect to the individual components of phase A. Similarly, V2 can be written as VA plus A square VA plus AVA. Right. Oh, sorry, VA. nahi. So sorry. VC, VB, VB, VC. by tracking how it is varying with respect to A, right? So this is how you decompose it into different sequence component and get the magnitude with respect to these symmetrical component. So this positive negative sequence will occur only when there is unbalancing in the system. And if there is unbalancing, we will be able to tell, okay, our system is not perfectly balanced. So this is what the instructor has used in its in this method as well. So what they are doing is they are tracking. Let's say, for example, if there is some voltage deviation, something happened in the circuit, and there is some power mismatch. This power mismatch will correspond to delta V, change in V, and this will give rise to negative sequence components, which is V2, right? And what they say is that let's track V2 by V1 in two conditions, pre-fault and post-fault. Not, I shouldn't say fault, it's pre-islanding and post-islanding, right? So it tracks this and then does a superimpose. When I say superimpose, it's just they take they just take how much is the deviation between the uh, uh, negative sequence impedance, right? So if they track this change with respect to negative sequence component and they come up with a new index which is able to give results as close as zero non as close as not zero perfect zero but near to zero non-detection zone, right? So these are corroborated by the findings in the instructor side. So the main essence that they use is if islanding happens, there will be change in voltage magnitudes, there will be change in this power mismatch in such a way that it will arise in unbalanced and not I mean it can be unbalanced before islanding too, but there will be some change in the negative sequence component if tracked could help you in give better results with respect to your this as an index, right? So this is called a ROCO SNSI superimposed negative impedance index, right? So these are this is one passive islanding technique that they have come up with in their research, right? Now another now there are some drawbacks too. One drawback could be, let me denote it by a negative, you know one drawback could be if the system is highly balanced. If the system is highly balanced, this will not work, because the negative sequence component will be very small. And if it is very small, tracking that small change will not give you perfect benefit, right? So the threshold matters a lot. How are you modeling the threshold with which you are checking if frequency has varied to that much, level or not? That threshold Modeling the threshold is difficult for a perfectly balanced system. So, so you have to model the threshold perfectly. So this is one drawback. I, I don't have many, it's just one. Right. So for this, now what we do is we've come up with hybrid islanding detection techniques which combine the advantages of both passive and active islanding detection technique. Right. So as you can see, uh, at zero power mismatch, when there is very less power mismatch, it is difficult to detect islanding conditions since electrical quantities variation is very less. Active islanding detection techniques, they drive the system into unstable mode or degrade power quality. In hybrid islanded detection techniques, system is monitored using passive IDT. When an island is predicted, it is further checked by active IDT. And this can result in significant reduction in power quality issues and also detection capabilities better than passive IDT. So we have here discussed one such hybrid islanding detection technique. So this is called voltage unbalance plus Rokoff. So this uses both, right? So what we do here is we check what is the voltage unbalance. So what is voltage unbalance? VU is nothing but ratio of negative sequence voltage negative sequence component of voltage to the positive sequence voltage component, right? We monitor this voltage unbalancing. So this part is passive. Sorry, no, this part is active, right? So what we do, no, 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 sorry, passive. What am I doing? This is passive. I'm sorry. Right. So we are monitoring the voltage unbalance and we check if it is over the acceptable limit. If no, that means there is no unbalance that has occurred and we can continue with our normal mode of operation. But let's say there is voltage unbalance detected, right? But it can so happen that it can be normal operation. Some component has tripped or something has happened and voltage unbalance has come. But it can be a normal mode of operation too, right? So to check if this is normal or not, what we do is we change the frequency. So this we are changing the frequency set point of our distributed generator. So it's done. This study is done for a 60 hertz system, which is American system. So what we do is we change it from 60 to 59, and we continuously monitor what the ROC of the system, rate of change of frequency, right? Or not rate of change. We just monitor change of frequency, if how the frequency is varying, frequency variation monitor. So this part is active. So we are inadvertently, so sorry, we are changing the set point in such a way that we are able to modulate the behavior of the distributed generation. Right, and then we check if the DG frequency has gone below 59.2. So we have changed the set point, right? So what will happen is if it is connected to the grid will try to change the operation in such a way that the DG comes back to the normal mode of operation. If it does not happen because main grid is not connected, it will go beyond the normal mode of operation, which is 59.3, right? So if it is that, what we do is we send a trip signal and we say that the PCC is no longer so the main grid is no longer connected. So let's strip the circuit breaker connected to the microgrid side, and we will change the frequency set point to the DG back to 60 hertz to track 60 hertz only. So this is one way in which we can model an active DT, right? So let me tell you. So there are two inferences from this. So what are the inferences? If VU alone exceeds the threshold. So only VU has changed the frequency operation, even though even if monitoring the frequency, it has not resulted in any unbalanced operation. So we can say some load imbalance has occurred. But system is normal. And let's say, yeah, the second inference will be both. If both change, if both are changing, what is happening? We are in islanded mode. So these are in some way the hybrid uh, islanding detection techniques work. Next, the last few lectures we discussed heavily upon how the interoperability comes into use in smart grids by using this communication infrastructure, right? We have communication infrastructure available with us, and if using this infrastructure we can check if we can make these circuit breakers, these relays, these switches to talk with different switches to tell if something has tripped or not. And by using this communication channels we can uh, detect if an islanding has happened or not. So the first one is power line carrier communication. So PLCC is an old form of it's an old form of I should say old technology. So in this, what we used to do is with our high voltage power lines, we used to have a high frequency, low energy communication line as well. So with HV power lines, we have a high frequency, low energy communication line. So this communication line is used to, communicate different equipments connected to this high voltage power lines, right? And why is this low energy? Because the H the power lines are usually, high voltage in nature, so that the signal does not distort. There is no EMI, electromagnetic inference with our system. We tend to keep the energy low. If the energy is low, we make sure that whatever communication we are passing, it's perfectly conveyed to the source, to the from the source to the receiver, right? So what we do in this and we can also have signal produced by disconnect. So we'll talk everything in, everything works on only two things, that there is a transmission and a receiver where they communicate with each other if something is stripped or not. So we can use SCADA, and we have synchrophasor based measurement units. Those are PMUs, right? So let's take the example of this. Let's say this is how our microgrid was working, right? And now this PCC, this main grid, sorry, this is PCC, and there is this main grid switch, and suddenly this main grid switch is now open. Once it's open, what will happen is that the transmitter, which is this, it will send a signal to the receiver. So this is transmitter and this is receiver. It will send a signal, okay, the switch has now tripped and you are now islanded. So this receiver will convey this to this inverter, that we are now behaving at a islanded mode of operation, and that you have to regulate the voltage and frequency on your own. So this is a form of signal produced by disconnect, where we use communication infrastructure to signal produced by disconnect, where we use communication infrastructure to send in signals. Similarly, there is this PMU based as well. So what we can do is, so these SCADA, these are steady state in nature, right? They convey messages in every 1 to 2 seconds. But PMUs, they are able to convey uh, 10 to 20 sorry 10 to 60 samples per cycle, right? So they have a higher resolution, so they can send more amount of samples per second. So we can use these PMUs, which are linked with respect to GPS, to convey if a relay to a relay if this voltage at point of common coupling, sorry, if this PCC is tripped or not, right? If the switch at this PCC is this circuit, sorry, I'm saying PCC will be this. If the circuit breaker has tripped or not, and we will be able to tell, okay, if the circuit breaker has tripped, it will tell this relay or this whatever this generator is over here, that okay, now you have to behave in an islanded mode of operation. So these are very easy to understand, yeah, but these are difficult to implement, because the amount of the high voltage lines and everything, they can cause a distortion in your signals uh, due to EMI, and they can uh, they may not serve their purpose for which they are used. So these are some detection techniques used, which are talked about in this in this week's lecture, right? So any doubts up until now? Any doubts? I, if you don't say anything, I'll take this as a no, okay? But if there are doubts, just unmute yourself anytime in between, and you can just ask it, shoot your doubts straight away. All right. So now we know if an islanding has happened or not, right? We can detect everything. But let's say due to some fault, something happened, and now your the integrity of your microgrid is in, you know uh, is in danger, right? It can so happen that this fault can cause certain damage to your microgrid as well. Some fault that occurs between, right? So now the standard protection equipments that are used in traditional grids cannot be straight away employed in your microgrids. There are certain issues that affect their integration to the microgrid, and these protection issues are dynamics and level of fault currents. We have bidirectional power flow and bidirectional current flow. We have generation and distribution side, right? And we can supply this generation back to the grid too. So due to this bidirectional power flow, we can have protection issues. We can also call false tripping of a feeder which is not supposed to be tripped, and we can have blinding of protection as well. So we'll discuss each of them one by one, but there are certain issues that arise in microgrid with which you will not be able to uh, make use of the standard equipment available at your disposal. So when I say a protection, when I say a protection device, what I mean is it should respond to both fault at utility and fault in microgrids. Then only it can be considered as a reliable protecting device, right? Last week we discussed what are the different metrics in which we we judge the level of protection we receive from the relays, and one of the metrics is reliability, right? And for this reliability there is inherent redundancy that we require, right? When I mean by redundancy is that you should not always be rely on single relay. You should have multiple backup relays to support that relay. When I say multiple, you shouldn't have infinite number of relays. I mean how much ever your it's optimal or cost is optimized. So these um, yeah, where was it? Yes. So there should be inherent redundancies, right? For example, your backup relays should come into play only when your main relays are not working, right? And that is how we will be able to tell if the system is or if the protection equipment is reliable or not, right? And the second thing is it must be able to isolate the smallest section of a feeder. Let's say a fault occurred, right? At one feeder, let's say this feeder. If I talk about feeder C, let's say feeder A, right? There is some fault, and one thing you can do is you can just simply trip this. You won't receive anything from your microgrid. You're fine, right? But that is not how you should do. You should only isolate that fault in that faulty feeder. Only that, not the entire system. And that is one thing in which your protection systems are usually, uh, you know, okay. So this is these are the basic basic attributes related to protection equipments. And now let's talk about these issues one by one. So these feeders or these figures display the issues that it will encounter. Let's talk about this. So let's say a fault has occurred, right? This fault occurred, and now uh, when a fault occurs, what happens is there is minimum impedance that generating device sees. A device sees minimum impedance. And how is that? Let me tell you how that happens. So we know V is equals to IZ, right? Now, what happens is at the fault location, the voltage collapses. If voltage collapses, this impedance becomes very less. So what happens from the grid perspective is that I see, okay, voltage is collapsing at that node. The the grid starts applying more power to so as to make sure that the voltage at that node is not collapsing, or that it's not going beyond its operating limit, right? So what we do is we supply to our maximum value that we can do, and that is precisely what happens. all the generators start supplying a fault current, which is for a synchronous base DRs, SBDR, it's 5 times the rated current. And for an inverter based DER, it's usually 1.1 to 1.5, but let's take a whole number for you, 2 times IR, right? So it starts applying this fault power to your, faulty current to your system, right? And to this fault. So there are three types of current that this fault experiences. One coming from your main grid, another from this generator 1, DG1, and second from this DG2. Now the magnitude that any relay experiences will be different for this fault, right? The synchronous based DR will supply 5 times, the grid will supply much more, this IBDR will supply twice the rated current, right? This magnitude will change. Like for example, in the grid connected mode this will be more, but let's say there is no grid connected, it's just an open circuit, the grid is not in picture. So only two, G1 and G2 are supplying this fault current, right? And they will supply up to their maximum extent, right? So the magnitude of the fault current in both islanded mode and grid connected mode is different. The magnitude from each G1 and G2 and the main grid, and magnitude with respect to the connection with the main grid, right? So because this dynamics is now changed, your relays should be able to adjust themselves based on what is happening with respect to re- uh, your uh, your system, right? That is why we discussed IDT, right? If the relay here, if let's say there is some relay here, if it knows it's not connected to a it's not connected to the main grid, it's islanded in nature, it will be able to tell with this much current only that if it is experiencing a fault or not. Earlier it was experiencing much more current due to the presence of capital IGF, but now it's only experiencing IG1F. So that is what why we discussed islanding before. Now there can be certain things like, for example, if let's say there are two kinds of fault happening, one at the feeder's end and one in the main grid, right? And both of them will supply power to the grid. Let's say for this fault one, the main grid is supplying IGF1, and this G1 is supplying some small IGF1, right? I should not use marker. This is not, yeah. So two faults happened, and it's now supplying this coming from the main grid and the small grid, and this G1 is also supplying to the fault location 2 as well, both of them. Now if you see the circuit breaker 2 here will experience a vector addition. If you do vector addition of sorry, I shouldn't say vector addition, yeah, I should say vector addition only, or algebraic subtraction of both of these. So what is happening, it will experience IGF1 minus small IGF2, right? So the amount of current it is experiencing for F1 fault is less than what it is supposed to, so it won't trip. Similarly, in this CB1 as well, because there is this current coming into because it's experiencing both this GF1 and GF2, it will not be able to tell if this, for circuit breaker 1, it won't be an issue, but for circuit breaker 2, this will be an issue because it is experiencing less current than it is supposed to. And that is why we require at least a sense of direction from where this fault current, if at all, is coming, if there are two currents coming into the play, right? So what we do is we install two different relays to check if there is some direction component based on if a fault has happened ahead of it or behind it. So that is how it is able to convey, okay, the amount of fault current you are experiencing is enough for you to trip now. So bidirectional flow causes this. Now there can be issues such as false tripping. What can happen is that, let's say this R1, it's a simple relay, it's not directional, it's not some directional component, it's just a simple relay. And now what happened was there is some fault in feeder 2, right? Now this G1 will supply this fault current, and some of that fault current will come from feeder 2 as well, right? So what can happen is this R2 will trip. It will trip because it has to trip because this fault is at feeder 2. But let's say if I have designed this relay poorly so as to experience only this much current that is coming, this green dashed line current, this current, if it experiences this much current, it will trip, right? So it's fault stripping. It should be able to tell if, let's say, the fault has occurred at its feeder or not. So that is where the sense of directional overcurrent relays comes into play, where we have a sense of direction as well as level. Similarly, it may so happen that relays connected upstream of the DERs. When I say upstream, it's above the DERs. So if, let's say, DR is here, relay is connected here, right? So let's say a fault has occurred. Right, this fault has occurred. Just a second. Hmm. So let's say a fault has occurred. Now, what is happening is that my G1 is supplying this fault current, and also main grid is supplying this IGF current, right? Now, what usually happens is that because there is some current component, so the fault current is not supposed to be, something. It's unique for every fault, right? Based on whatever it is behaving, right? Due to this presence of IGF, the capital IGF will not be such that, let, how should I should be able to explain it better like this way. Let's say, not like this. Let's say the fault happened here, or let's say here. The fault happened. What really will happen? There is some fault current coming from this side, but main current will come from this capital IGF, right? This will experience a higher level of current compared to what it is experiencing right now, because of the presence of this smaller IGF component. So it won't see the level of current which it is supposed to see for tripping the circuit breaker 1, right? And this is what is called blinding of protection in microgrid. This usually happens at upstream relays connected directly across the substation, where it is unable to tell if, let's say, the fault has occurred behind it or in front of it. Sorry, if the fault has occurred or not, because it's not seeing the level of fault current it is meant to see. So this is one way in which these relays suffer. The protection relay suffers in this, and that is why we should be able to come up with newer schemes at our disposal, right? So let's take an example of this, right? Sir, what? Yeah, yeah. Sorry for interruption. No, then how we will solve these issues? Yeah, yeah, we'll discuss. We're coming to that. So we use both kinds of. So we need a sense of direction, a sense of overcurrent, right? And for that we use directional overcurrent relays, which use the mechanics of both directional relays and overcurrent relays. So it was not covered in this week's lecture. It will be covered in next week. But what we use is called directional overcurrent relay, where we map the direction of the fault as well as the level of the fault current that it is supposed to oversee. So we'll come, I mean, that is the next slide. Hmm. So let's say just an illustrative example to see if everyone knows how fault stripping or everything behaves, right? Because I know it can be a lot of information for a small class. So I have to cover 5 lectures in 1 or 2 hour, and it is very difficult for me to convey everything, right? So you have to see those lectures, and then I will be able to better tell you how uh, you know this is a doubt clearing session. It's not something I'm going to teach you fresh, right? It will be very different. Okay. Yeah. No, I'm not just talking to you, I'm talking to everyone. Yeah. Let's see that let's see using this example here, we have a synchronous based DR and an inverter based DR connected at two different points, and a fault has occurred. Right, what I want to get from this exercise is which relays are prone to, sorry, which relays are prone to, one, magnitude of fault current, second, bidirectional fault current. Oh, bidirectional will cover in magnitude and bidirectional, right? Because this fault is not. Hmm. And we have fault stripping, and which relay will be blind. So now we will check which of these relays will suffer. Um, using this simple experiment, right? So let's see. Now, as I already told you, so a synchronous based DR supplies 5 times the rated current as fault current, and an inverter based DR it supplies twice the rated current as fault current. In If you check IEEE 1547's standard, it is 1.1 to 1.5, but to take it as a whole number, 2 is generally used as a, you know, as a thumb rule. Okay, so where was I? Yes. So, which of these relays do you think are prone to the magnitude of fault current, which will not be able to, judge the dynamics in the level of fault current? I should write dynamics of the level. It is what is written in the dynamics, right? So let's see. Let's say that there was no synchronous base DR here, right? Now, if this synchronous base DR was not there, for this fault at this feeder, the relay 5 will sense a smaller current compared to what it is now sensing because of the presence of this SBDR. That is what is shown over here, right? This green one is coming into the play and it is sensing more current than usual. So let's say if SBDR was not there at all, right? If this synchronous based DR is not there, the R5, because this fault has occurred directly in front of it, will be the most sensitive to the dynamics of the fault current. So the closest, not closest, but the one that is seeing changing dynamics of the DER and other things in the system will suffer the most, right? Let's say that this was not there in picture. This relay 5 will not be able to tell if this has tripped or not, because let's say it's set up for a current. If IR5 is set to experience IFR5 with SBD, right? If it is set to experience this current, it will not be able to sense if this feeder is not connected, right? So relay 5 is most sensitive to the dynamics of fault current. Now let's do the second one. Who can tell me which relay is more prone to false tripping? So you have to think from the perspective of, how and what happens during this, right? So who can tell me? So for this fault, what is happening? So the synchronous based DR is supplying 5 times the rated current, right? R3 and R4, right? So it is supplying the same fault current that it is supposed to see. The R3 and R4 are supposed to see this ISBD fault current, and it is seeing this, right? Let's say fault occurs here. Both R4 and R3 will see ISBDF, right? And it is supposed to trip, but it's not. Let's say it's not modeled to. Let's say this fault is not happening here; it's happening here. So still, it is seeing the same fault current that it is supposed to see, and it is more prone to the false tripping. So R3 and R4. Which one will be blinded? So I already told you the one that is upstream will be blinded, connected to. So the thumb rule is with the one that is connected directly across the substation, that will be the most that will be blinded the most. So R1 will forever be blinded by this protection, but R6 as well. Let's say some fault occurred here, right? Sorry, yeah. So this fault occurred here, right? Even if this fault occurred at this side, that R1 is here, this S6 will supply the same fault current. And let's say it is not set to experience this level of fault current, it will be blinded by any fault that is happening over here, and it will continue to supply the same fault current. So R1 and R6, the one connected directly across the substation and the upstream DRs are um, mostly blinded by this relay. So now we know that our relays must be able to sense the direction as well as the um magnitude of the current, right? The fault current. So for this, we use a combination of overcurrent relay and directional relay, also called as directional overcurrent relay. The all the analysis will be discussed in the next week. It just the instructor gave a brief overview of what both of these relays are. We'll just cover what the brief overview is, but the whole analysis will be covered in the next week. Right, what does an overcurrent relay do? An overcurrent relay generally is connected across a CT. CT is used to sense the current. It is a current transformer. It senses current. It scales it down to, some level 5 ampere, which is the standard of current for relays is 1 ampere and 5 ampere, right? And standard of relay voltage is 110 degree, 110 voltage phase to phase. Right. So CT converts it down to a scalable level, which can be easily sensed by this relay. And what it does is it checks if the magnitude of the found voltage, let's say the found voltage is IF, and it checks with a polarizing quantity. It's called a polarizing quantity with respect to IP. What is the fault current? If IF is greater than IP, this overcurrent relay will send a trip signal. But if it is less than this, it will not send a trip signal. No signal. So this is how an overcurrent relay works. And this overcurrent relay is generally IDMT in nature, which is inverse definite minimum time. That means with respect to with increase in fault current, the time taken to trip also changes. So if let's say the fault current increases, the time taken to trip will also decrease, sorry. So that is, there is an inverse relation. That is why they are called inverse definite minimum time relays, right? And in a directional relay, what we do is we take the voltage at that bus at which it is connected as a polarizing quantity, and we check the positive and we check the fault currents and their phase angle with respect to this polarizing quantity, which is the voltage, right? if this if this phase angle found, if phi found is 0 to 180 degree, or if it is 180 to 360 degree, right? It's not visible, I feel. I'll use a next page. So directional relay, what they do is they have, okay, so they have both CT and PT. PT is used to sense voltage at bus, and CT is used to sense current. Now, the phase angle with respect to this polarizing quantity, which is voltage at that bus, is used to see if how the what should I say, how the phase angle lies with respect to the voltage. And let's say phi is between 0 to 180 degree. We say that fault is behind the relay. This is general standard. And if it is 180 to 360 degree, we say fault is in front of the relay. So we use this you know kind of like a standard to check if, let's say, the fault is happening behind it or in front of it. And that is how a directional relay works. So for our microgrids, we require both. We require a relay to sense both the current if it is increasing or the direction if it is changing, right? And that is why we use directional overcurrent relays. And the dynamics and everything related to overcurrent relay and directional relay will be discussed in the next lecture or next week. Right, so this is what the instructor has discussed in this week. And um, yeah, so we started with microgrid. We discussed what are the different islanding detection techniques and why islanding detection techniques are required. We discussed the various issues, and we discussed various passive islanding detection techniques, active, and then uh, hybrid islanding detection technique. We also discussed communication-based islanding detection techniques, and then we moved on to smart grid protection, microgrid protection. And we discussed what are the different issues that it faces and how a DOCR or a directional overcurrent relay can be used to, uh, have an effect over it. So this is all that I wanted to cover for this week. So again, I will give this disclaimer. These are not a substitute of the lectures that are covered in NPTEL. I cannot cover 5 hours, right? Some 2 3 hours of lecture material in a single 1.5 hour class, because I have to cover question and answers too, because it's a problem solving session. And I will always be, grateful if you can watch these lectures, and then we can have a discussion, because how I explain things is with respect to if you have gone through that lecture or not, because I cannot start everything from scratch. Okay, so I hope that this was clear to all of you, and if there are any questions, I would open the floor, and then we can discuss question and answers. So if there are any questions, please let me know. Any questions? Just unmute yourself if there are any.
Clear, sir. Nothing.
Okay.
I said.
Okay. Okay, let's discuss questions. So we covered everything, right? So now I want you to, answer everything as well. So my involvement will be very limited. So the first question is very easy. If a microgrid has an 800 kilowatt load and a 200 kilowatt solar generation capacity, what is the power imbalance it will experience when the island is when the microgrid is behaving islanded? So it's very easy, right? So your PMG is given, your P load is given 800, 200. Mm, I'm afraid that's not the correct answer. So I told you here, right? So what is the mismatch? So the mismatch is, what is the difference between, oh, so yeah, 600 is the correct answer. Yes, yes. So we are checking how much it was, how much power it was taking from the grid, which is how much? 600 kilowatts, right? And if it is now behaving islanded, the 600 is the power imbalance that has occurred. So the correct answer is C. Yeah, second, the rate of change of frequency islanding detection or ROCOF is affected by. So who can answer this question? It's very straightforward. So I have covered everything. So so ROCOF is what? Delta P upon 2H, right, in per unit form. So generator inertia constant is directly affecting it. This is the correct answer. Now the type of load connected. So what do you mean by type of load connected? Let's say that there are um, okay, so if let's say there are high volume load connected, let's say some industrial loads, and they suddenly a power imbalance has occurred, and these loads are now lost. So when these go away, the delta P increases with the kind of volume that they were supplying, right? Similarly, if there are power electronics based load based on solid state switching and solid state switching devices, these are very fast acting resources, right? And if they cause imbalances, they directly affect the change of they directly affect the frequency as well, right? So the Rokoff is dependent on the kind of load connected to the system. So the correct answer is C, both A and B. Next, the presence of real and reactive power mismatch leads to change in dash in islanded microgrid. So if there is both real and reactive power mismatch, what will happen? Delta. Yeah. Yeah, someone was saying. Yeah, Naki, we are unable to hear you. So can you use chat box? Yeah, we are unable to hear you. Yeah, so we've covered this thoroughly in today's class. So I feel everyone should answer. Frequency, okay. So it's both real and reactive power mismatch. If both are there, see this figure, right? Okay, so let me tell you one thing very quickly. So delta P will affect delta F and delta Q affects delta V. The voltage magnitude is directly affected by the change of reactive power in the system, and the change in real power affects the change in frequency. Directly from this equation, you can see, okay, rate of change of frequency is directly proportional to delta P. In delta Q, what happens is the amount of reactive power in the system, you've seen capacitor supplying reactive power, it increases the voltage at a particular node, right? We'll discuss in next few weeks when we'll discuss group control why this happens, but just bear with me for a few seconds that change in reactive power affects the change in voltage. So if there is both kind of mismatch where there is real and reactive power mismatch, both of these will be effective, both frequency and voltage. So Naki, I think the answer would be both of these, no? There's both real and reactive power mismatch. So this was a very easy question. I'm afraid why people are not responding. So yeah, Naki, go ahead. So are you writing something? Got it. Okay. Yeah. So right. So there is both real and reactive power mismatch, and we discussed here as well, right? In this section, that change in delta Q affects voltage and change in delta P affects frequency. And that is why there is, set points derived for both of these mismatches. Next, which of the following is not a feature of microgrid? Who can answer this? S- Government incentives. Okay, so microgrids increase system reliability. This we all know, right? Second, they are environment friendly in nature. Now let's talk about incentives. So you see, government is giving incentives right now for getting, installing solar PVs at offices, at every place you'll see that government is giving incentives or subsidies in form of subsidies for you to install solar rooftop panels, right? Next, in any case, let's say we want to supply a village or a hamlet which has not been energized before. So IIT Kanpur, at least we energized two hamlets near Kanpur region where there was no electricity since the beginning, right? And it was very difficult to get electricity over there because that was very far from where the nearest substation was, and nobody has paid attention. The villagers were living without any electricity since the beginning, right? So what we did was, with the help of government, we installed two microgrids over there. So government wants to install microgrids, because a substation is not feasible at all points at all places. And these microgrids, they can self-sustain themselves without the need of main grid if they have sufficient generation available to empower the loads, right? So the government is handing out incentives, and this was covered in the slides as well. Less energy efficiency is where is not a feature where these are energy efficient in nature, because we are able to make use of solar energy which is available during daylight by tapping them in the form of from the solar PV in the form of electrical energy, right? So they have energy efficiency, and we don't require power from grid at all times. We can supply localized generation by using these localized sources of generation, right? So does that make sense? I think government incentives, we all know, right? The government wants to increase the penetration of renewable energy, and it's therefore providing incentives for you to install it in your households, and also as form of standalone solar PVs and stuff like that. So government is providing incentives. Yeah, so Naki, we are on the same page, then only I'll move ahead. So if anyone has a question, can just ask me here. I mean, okay. So I'll move ahead. If you have doubts, you just unmute yourself and let me know. Next, failure to detect unintentional islanding events impose which of the following events? Who can answer this? So we covered here, right? So if we have a failure in detecting the unintentional eye landing, so I'm online, right? Nobody is responding, so I guess okay, I'll continue. So yeah, where was I? So failure to detect unintentional eye landing events, these can lead to malfunction of protective devices. We already know if how it happens. I've covered in depth. Next, it can lead to equipment damage. Oh, should not. Yeah, it's a wrong answer. Yeah, it can. Sorry, I should do this. It can cause equipment damage because power quality deteriorates if there is an islanding, and due to this, if it is unintentional in nature, power quality will deteriorate, and if power quality deteriorates, your equipment can get damaged, and threats to personal or crewman security safety. And if let's say someone is working on that line, and if it is unintentionally removed or auto reconnected, this can cause uh, 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 this can be fatal for that personnel, right? So the answer would be all of the above. Next, in context of power quality monitoring, inverters work on PWM principles and generate what? So I already told you. So inverters, they have, so I just showed square waveform. It can be triangular, and then there is 120-degree conduction mode, 180-degree conduction mode. There is space vector pulse with modulation as well. So there are different PWM techniques. But what usually happens is that they lead to harmonics, and these harmonics are higher order in nature. See, yes. When I say higher order, is it's that they are greater. They are normally very they lie outside the normal comprehensible zone, right? And you can easily use a low pass filter to extinguish these harmonics, right? And that is how inverters should behave. They should have higher order harmonics only. If they have low harmonics, it the power quality uh, will be very bad, and it's there's no fun of using inverters then, because we require closer to how our AC voltage is behaving, right? Perfect sinusoid voltage. So they have higher order harmonics. Fourth, in which of the following IDTs is the DR driven into unstable mode? This we covered at length. So there's only one answer to this. We deliberately, we deliberately provide a wrong feedback which can lead to a positive feedback into inside the system, so that not wrong feedback. We shift the frequency or voltage in such a way that it causes a positive feedback that leads to the DR being driven into unstable mode, and that happens in positive feedback technique. So we discussed at length. I don't know why you're not answering so. Fifth, which of the following IDTs make use of technologies like SCADA or PLCC? Who can answer this for me? So power line carrier communication and supervisory control and data acquisition is used in. It's used in communication islanding technique, no? Why hybrid? So we used here, na? Communication. These are yes, yes. So these are communication based IDTs, right? So this communication based islanding techniques. Next, power line carrier communication uses a dash energy communication signal along the high power line. So power line carries high voltage. So these are high voltage lines, right? So if you don't want EMI to propagate to your communication, what kind of energy signal should you use? You should use a high frequency, low energy communication signal, right? So that the effect of deterioration is less. So the answer is low. Second, voltage unbalance can be expressed by, I told you, VU is what? What is the ratio of VU? So I told you already it's ratio. So these two can't be the correct answer. So what is the correct answer? Okay, so no one is telling why. I just discussed everything. I don't know why you're not, you know, it pains me. So here I told you what is it? It takes negative sequence to positive sequence. You're right. Yeah, right. So we covered everything in I covered symmetrical components as well. So okay. So it's V2 by V1, which is negative sequence by positive sequence, right? Next, eighth. Which of the following is or are protection issues in smart grid? This everyone should be able to answer. D. Okay. So both, all three. So all of these is the correct answer. So the penetration of DRs not only changes the dash of fault current. Yeah. So both of these, it changes the level as well as the direction, and that is why we want both overcurrent as well as directional relays. And the overcurrent relay should possess, if it is, something to be able to change the polarizing quantity in such a way that it is able to detect if the level has changed or not. Last, the utility grid contribution to the fault current is dash due to the contribution from DG resources. So we said, right, if let's say the fault current is being supplied by both the main grid as well as the DGs, so the fault current at the main grid will be less than what it is supposed to be, right? So the contribution is reduced, and that is why the blinded relays happen, because they are not able to sense, okay, if some fault has taken place or not, because the level of current is less. Yes, so the answer is reduced, B. Right, so we covered everything, I guess. So yeah, we started with what is microgrid, why islanding is required, what is islanding first of all, and why islanding is required. Then we discussed various islanding detection techniques, and then we moved on to smart grid protection schemes, and we discussed how the the presence of DGs at the distribution side is is causing issues in the protection schemes, traditional protection schemes, which cannot be employed without adapting it to the newer, or with newer schemes, right? And for this, we stopped here, but yeah, we'll continue our discussion in the next week, where we'll first discuss what are these different kinds of relays and how do they work, and how newer kind of relays are being how newer kind of relays and newer algorithms are being implemented to implement or adapt their application to microgrids, right? So if there are any questions, the floor is open. Otherwise, we'll just end the meeting for today. Any questions?
Sir, these slides will upload today or
Yeah, I, I'll upload these slides. I mean, I always upload.
already upload? Okay,
No, no,
thank you.
no. I always upload. I'm uploading it right now.
Already.
Yeah.
Yeah. Okay.
Anything else?
Nothing, sir, from my side. Thanks.
Okay. Okay. So if there are no doubts, yeah, I'll see you next week probably. So bear with this, right? I mean, you may think that you're not getting a lot of stuff, but I will tell you, go through the lecture videos and then come to this lecture session, so that we can talk and remove your doubts, if any. Otherwise it will be just me sitting here revising everything without even knowing if you are understanding or not, right? So just that is what I'll and that is the note I'll end this class with. So thank you all for coming and joining the session. Thank you very much. Bye bye.
Thank you. Bye.
Bye.